Then let us continue the rest of the part. Then we have very interesting tutorial for this. So that also let us solve. Yeah. Okay. So as you know, any state of particular thermodynamic system should be represented by certain properties. Yeah. So again, when the process is taking place, it is changing its state from state 1 to the state 2 or state 2 to the state 3. Again, we will be defining with certain state parameters. Okay. So that is the reason we need certain system which representing its properties and its relations. Okay. When phase change is happening, then how to calculate these all properties and all. These all we are reading in this particular chapter. So first of all, what is the pure substance? The pure substance is its composition will not be changing throughout. However, it's changing its phase based upon the pressure and temperature. Okay, that is pure substance. Suppose refrigerant which we are using in case of our air conditioning systems and refrigeration systems. Okay, we have many problems upon that also we will be solving, then you will be getting very clear idea. Then steam, which is the major substance or working fluid in case of our thermal plants. Okay, apart from this, any substance which is just changing the phase but composition is not changing, even ammonia. Okay, in refrigerants also many refrigerants are there like that. Okay, so if you see over here, this phase change of pure substances would be represented upon this PVD diagram like this. Okay, this is three-dimensional diagram. This diagram we will be representing in three ways also, like PV or VT or PT. Okay, like this. Okay, now let us discuss one by one. Suppose see, this is your TV diagram. Okay, so any substance, pure substance, what we have assumed its composition is same, but it's changing its phase that we have represented, right? So how it is changing the phase, that let us see. See here, when you are considering pressure as the constant, when you keep on supplying the heat, okay, initial stage we can call it as subcooled. Okay, then at one point, this point we can call it as saturated liquid. Okay, then at that point temperature will be remains constant. Okay, and pressure also will be remains constant. Then phase change is happening like this way. Okay, phase change is happening. This process, whatever here, whatever the heat we are supplying, that we can call latent heat supply. At this point, this is completely or otherwise 100% vapor state. That's what we can call it as saturated vapor. So this point is saturated liquid, this point is saturated vapor. Okay, after the saturated vapor, still we are supplying the heat. Okay, it is completely vapor. What is happening now? Only the vapor temperature is further increasing. This we can call it as superheated. Okay, superheated vapor. This is the superheated region and this is latent heat region. This is subcooled region. Okay, and if you observe over here, when you are increasing the pressure, suppose this is 1 atmospheric pressure we have taken. Okay, and this thing we are considering for water. Okay. So in that case, as you know very well, at the means atmospheric pressure, the boiling temperature of the water is 100 degrees centigrade. Okay. When you keep on increasing the pressure, okay, this latent heat pot is reducing. Why? Because with increasing the pressure, the volume is decreasing. Okay, the heat entrapment in this particular zone is also increasing. Yet one point, this is the point. Okay, latent heat is completely zero. The liquid is converting to the steam without this in between mixer state. Okay, in between the mixer state. Mixer state means liquid plus vapor. Okay, without this directly. So whatever the power plants we run above this, we can call it as ultra power plant. Okay, above the critical point we are running, suppose. So now the issue is when you are operating certain cycle. Okay, when you are operating certain cycle, that cycle could be refrigeration cycle or that cycle could be power cycle like steam thermal power plant. We will be operating our fluid such a way that it will be in all the zones. Okay, it will be in sometimes in the mixer zone, sometime will be subcooled zone, sometime will be superheated zone. Yes, so superheated zone, then after we are impinging upon the turbine. Okay, then it is coming like this. Okay, then it will be obviously like this. Okay, then it is coming in the mixer zone again, then it is passing to the condenser. Then condenser purpose itself is to change the phase, that steam is converted to the liquid, and again that liquid is pumping back to the boiler. Okay, and it is heating. Okay, and again the boiler is gaining so much of heat from the combustion source, then it is changing its phase again, like this process. Okay, so like this many processes or many points will be achieving in case of any refrigeration cycle or otherwise power cycle. Okay, so now the thing is how to calculate properties wherever you want. Okay, point here, point here, anywhere. That is our study in this particular chapter. Okay, so apart from the critical point, there is another point, that is the triple point we have mentioned in our previous class also. What is happening over here? Here, the solid to the liquid, liquid to the vapor. Okay, that is when you maintain the pressure as the constant, when you supplying the heat. Yes, so suppose take the ice at room temperature, sorry, atmospheric pressure. Okay, take the ice at atmospheric pressure, its temperature may be less than 0. Okay, -5, -10, based upon the whatever the temperature you have cooled up to. Yes, then you are giving the heat, then slowly ice is changing to liquid, then liquid is changing to steam. Okay, but still you are maintaining the temperature, sorry, pressure as the room atmospheric pressure. Okay, so that time the line will be appearing over here, but here one process is there, directly solid to the vapor. Okay, without passing to the liquid, below the triple point it is happening. Okay, so that is actually happening in case of dry ice. Okay, that means carbon dioxide blocks. Okay, and even naphthalene balls. Okay, these all are without passing to the liquid stage, the solid directly evaporating. Okay, that process we can call it as sublimation. Anyhow, we are not studying any properties in the sublimation zone, because we are not using that kind of phenomena anywhere over here in any applications of thermodynamics now. Okay, some other applications are there, but not in the syllabus. But this solid to the liquid, liquid to the vapor is very common applications. Okay, majorly liquid to the vapor, which is our refrigeration cycle. Okay, that with refrigerants of chlorofluoros or ammonia refrigerant, or even your steam thermal power plant. These all are operating in this zone. Liquid to the vapor, vapor to the liquid, coming, going, coming, going in this between. Okay. Okay. So these are that we have already discussed. So whatever that 3D PVT plot. Okay, so we have divided into PV, TV, okay, PT. Okay, and now, so when your liquid is changing the phase, okay, from saturation liquid to the saturation vapor, in between, if you observe, in case of latent heat zone, okay, this is the latent heat zone, these are different pressures. Okay, in the latent heat zone we will be observing certain fraction of liquid, certain fraction of, rest of the fraction is vapor. Okay, so as like that, at any condition, this condition or this condition or any condition, we need to calculate how much amount of liquid is there and how much amount of vapor is there. Okay, that dryness fraction we call it as. Okay, these all are more elaborated way. I would like to give you much information. That's what I have typed text over here. Okay, point by point you can read it. Okay, these are the things again over here. This is okay. This is the dryness fraction or mixer fraction we are calculating over here. That is mass of the vapor. Okay, in the container. Suppose see, this is saturated liquid and this is saturated vapor. Okay, in between we have, in the latent heat zone we have combination of both water plus liquid, is it? So here, what is amount of the water divided by total mass? This is obviously total mass, that we can call dryness fraction. Based upon this, your properties will be changing. Okay, whatever the dryness fraction, because the specific heat of steam is different, the specific heat of water is different. Okay, at one point certain amount of, in the latent heat zone, at one point certain amount of mass is in the vapor stage, certain remaining amount of mass is in the liquid stage. Okay, then if you want to calculate over there enthalpy or heat content, okay, then you mustn't have this data. Anyhow, we are going to see how to calculate those all, and also we are going to calculate or otherwise see many tutorial problems also today. Okay, okay, so for this purpose, okay, for this purpose, at different, suppose if you see any plot like this, okay, so here we have many pressures, okay, at many temperatures, even not only for particular fluid or otherwise particular pure substance like water. Okay, many other gases also there. Okay, so at every point we should have data like what is specific volume of saturated liquid at this particular pressure, what is specific volume of saturated vapor at this particular pressure. Okay, if you know in between the mixer fraction, then we can use. Okay, like that, different pressures, different temperatures, even suppose see here this is vapor. Okay, we are sure it is in the superheated zone. Yes, this is in the superheated zone. At this particular point, obviously the temperature is more than the saturation temperature. Yes, that's what we are calling it as superheated. Okay, at this point, the volume would be more. Yes, volume would be more. Enthalpy would be more. What is the enthalpy we are going to see? Okay, otherwise heat content. Okay, heat content would be more. So like this, at different pressures, different temperatures. Okay, so we should have data not only for one particular substance, for many substances. Regarding this, certain tables are available. In case of water, that we can call it as steam tables. Okay, for other gases we can call it as gas tables. Okay, that book I have pasted you, means I have uploaded in our teams. Okay, At the end of that book, you can find out table A1, table A2, table A3. Okay. Table A2, table A3 are for the steam specially. Okay. So please open now and you can see that. Okay. I'm giving you 1 minute or couple of minutes. So please open, or shall I open it and show you? I think not required. You will be opening that and you can see. Can anyone confirm me once you find out? Because those only the tables we are going to use in our now the problems. At the end of the textbook, you have the tables, table A1, table A2, table A3, like that many tables we have. Okay, have a look. Table A2, table A3 are for steam tables, we can call them. Okay, and after that also superheated steam table also there, and different gases like refrigerant 22, okay, refrigerant 134, okay, even ammonia, okay, like that different gases are there. Could you able to see?
Sir, could you repeat the table numbers again?
Yeah, tables at the end of your textbook, we have some tables, table A1, table A2, table A3, like that. Table A2, table A3 are for the steam tables. Yeah. So could you able to find those tables?
Yes, sir, like properties of saturated water and
Yeah,
everything.
if you find, then the table would be like this. Yes, in the slide whatever I'm showing here, okay, it would be given pressure, temperature, okay. So in the slide I'm showing over here, VF, F means liquid actually, okay. So specific volume of the liquid, okay, or saturated volume of liquid, and even specific volume at saturated gas, okay, and even this is internal energy, specific internal energy of saturated liquid, specific internal energy at saturated gas, okay, or vapor we can call it as enthalpy, okay, specific enthalpy of saturated liquid, specific enthalpy of saturated vapor, and even these two are entropies. Okay. Anyhow, in this chapter, we are not going to touch this entropy part. Whenever entropy chapter will come, that time let us see. Okay. Like this, you will be finding out these are the steam tables. Okay. The same table, similar kind of tables you can find out for many gases at the same place. Table A4, A5, A6, A7. Okay. Like that, many tables are there. Okay. Anyhow, anyhow, we are going to use them also in our tutorial now. Okay. Now, so whatever the table you have seen, okay. So in the table, certain pressure interval they have given, or otherwise certain temperature interval they have given. Okay. But in your calculations, you need in between of certain pressure range, or you need to find out the details of certain temperature, okay, which is coming in between the range. That time you have to take linear interpolation. Okay, simply linear interpolation. How accurate is the linear interpolation? Means it is accurate but not appropriately. Okay, but however, this is the common phenomena we use when calculating for any. Suppose this is 200, this is 250, this is 240. Okay, in between, suppose if you want 207. Okay, or otherwise this is 200 and this is 240. If you need data in between 215, we will be considering simply a linear interpolation. Okay. Once you know dryness fraction, okay, suppose your point is there somewhere in the latent heat zone, okay, somewhere in the latent heat zone, like this here, suppose. Okay, here first you will be calculating x. Okay, what is the dryness fraction. Once you calculate the X, then here at the mixer, you will be calculating specific volume. Okay, the specific volume obviously greater than specific volume of saturated liquid and obviously less than specific volume of saturated gas. How much it would be? Okay, that is obviously function of your dryness fraction. Okay, so this way we will be calculating. Okay, this is specific volume of saturated liquid plus dryness fraction. Okay, X, then Vg minus Vf. Vg means specific volume of saturated gas. Okay, like this is the phenomena we are doing for specific volume. Same phenomena we will be repeating for all other like enthalpy. Okay, so here enthalpy, many times we have discussed about this enthalpy. Discussed means we have pronounced that word enthalpy. Enthalpy, what is enthalpy? So enthalpy is simply the summation of internal energy plus multiplication of pressure and volume. Okay, this is just one word, or otherwise we have added these certain things in case of thermodynamics textbooks. Okay, that is enthalpy. So here this you can consider per unit basis, mass basis, and representation actually. Otherwise, the formula is same. Different ways of representation you will be finding out in the textbook. When we are taking per mass basis, we will be using small h. Per mole basis, we will be using bar over here. Okay, that is about that. These are the steam tables just now I have explained. Okay, the same like that way. You will be, as we have calculated earlier, the mixer specific volume. Here we are calculating the mixer internal energy. Okay, here internal energy of saturated fluid plus dryness fraction and difference of both. Okay, that means at particular pressure, at particular temperature, these two values Vf and Vg, means Uf and Ug. These values you can get from your steam table, and then X value we will be calculating from the given data. Okay, that way you will be calculating anywhere in the, means in the latent heat zone, the mixer internal energy. Same way, the mixture enthalpy also we will be calculating like this. Okay. Now, I'm sorry. Now, specific heat. Okay, this you know very well because you might have practiced this thing in case of your class 11 and class 12 also. It is like amount of energy required to raise the substance temperature of 1 degree. Okay, that is specific heat. Even this specific heat is different for different materials. Okay, so different fluids or different materials. Okay, however, again the specific heat of certain material will be varying based upon whether the process is going with a means constant pressure or constant volume. Okay, now the specific heat at constant volume and specific heat at constant pressure, both are actually intensive properties. Okay, and these two are specific heat at constant volume is function of entropy, sorry, internal energy. Okay, and specific heat at constant pressure is function of enthalpy. Okay, why? Because specific heat at constant volume, why only internal energy means once you take over here this equation, yeah, here this equation. Okay, in case of constant volume, there is no change in the volume. Okay, that would be 0. Okay, that's what for case of constant volume. Okay, the specific heat is only function of internal energy. Okay. For case of the constant pressure, pressure would be constant, but volume will be changing. That's what the Cp is function of enthalpy. Okay. Enthalpy means again it is coming with both. What are these both? And even temperature, pressure, internal energy, everything. Okay. Now this concept of specific heat at constant volume, specific heat at constant pressure. Okay. So these two can be applicable to which kind of the fluids or what kind of the materials, not fluids actually, what kind of the materials. The simply we can say if the material is not compressible, okay, it is not compressing at all, then where is the matter of process at constant volume, process at constant pressure? Okay, so those materials we can call incompressible materials. Okay, in that case, what we are defining, volume change is zero. If it is incompressible, like solid, like solid. So that is the reason there is no matter over here whether it is Cp or Cv. In case of incompressible material, we will be considering it as only specific heat C only. Okay, that is fine. Now let us go to the compressible materials. Okay, compressible materials where Cp, Cv both are coming. Okay, and also since it is the gas, there is the question about whether it is the real gas or ideal gas. You might have heard these all the things also. Yes, whether considering to the real gas or otherwise considering to the ideal gas. Okay, that we are going to see.
Sir,
This is where, yeah, please.
sir, for solids you said that the Cp equal to Cv. Sir, but when if suppose we evaporate iron, sir, then Cp.
Yeah, yeah. That yeah. When it is changing the phase, then it is coming liquid stage, right? That is not no more solid.
Yes, sir. Yes,
Yeah,
sir.
yeah. That time again, these all will be coming. Okay. Whenever you are calculating or assuming your problem is going upon, okay, if it is still in the solid stage only or still in the liquid stage only, liquid also not compressible. Okay, that time we will be considering. When it is changing the phase, okay, so in that entire range you will be considering, then CPCV will be varying.
Okay, sir.
Okay. So now, okay, let us study about real gases and ideal gases. Very interesting topic. Okay, now see, many times we have used universal gas constant and we have used that value as 8.314 kilojoule per kilomole Kelvin. Okay, why? Okay, and also why this is the universal. For any gas we will be using this. Okay, so this is the concept. Okay, this is the concept. So in a piston cylinder arrangement, take certain gas, okay, and try to maintain I'm sorry, try to maintain that gas temperature all the time constant. Okay, wherever you have taken suppose T. Okay, then reduce the pressure, keep on reducing the pressure towards zero. Okay, then it will touch on one point over here. Okay, this point let us consider R. Okay, okay, if you practice this particular process for the same gas by maintaining different temperatures. Okay, in the piston cylinder assembly of gas, you might have taken certain high temperature, certain low temperature, certain low temperature, certain more low temperature. Okay, for all the cases, you will be operating such a way. Okay, whatever arrangements need to be done, those all things are another issue. Okay, and you will be moving the piston cylinder pressure, making it moving towards almost zero. In that case, this will be touching at this point. This point will be same for any temperature, Not only for that, for any gas also. Okay, if you follow this particular process for any gas, that also would be touching at the same point. That is the value this much. That is the reason we are calling it as universal gas constant for any gas. Okay. Now out of this, we are defining compressibility factor. Okay. Out of this, we are defining compressibility factor like this. Okay. So PV by T. Okay. PV by T it is. And that itself is R. Okay. So now we are dividing this by this. That we are calling it as Z. That we are taking it as compressibility factor. Fine. Whenever compressibility factor of certain gas is equal to 1, that gas we will be considering it as ideal gas. Okay. If compressibility factor Z of certain gas is above 1 or below 1, those all are we are considering it as real gas. Okay. But see, all gases can be real gas and same time can be ideal gas, but that depends upon the particular operating conditions. Means particular condition. Suppose see, this is this is for hydrogen actually. This is for hydrogen. The same procedure whatever we have assumed that we are repeating over here. Okay. Suppose we are maintaining the temperature as a constant 35 and ranging from room temperature of 300 Kelvin. Okay. And pressure we are varying like this. Then what is happening over here? At certain cases, Z equal to 1 for certain temperatures. Okay. Irrespective, one thing you have to observe, irrespective of the temperature, okay, irrespective of the temperature, at very low pressures, okay, at very low pressures means in this zone, okay, all means whatever this particular hydrogen gas at any temperature is behaving like ideal gas. Yes, is behaving like ideal gas. Okay. That means gas temperature, the operating pressure, okay, these are defining whether the gas is at ideal gas or real gas by the help of Z factor we are considering. Oh, what happened? Happened. Okay. Okay. So now whatever this plot, whatever we have over here, this is for hydrogen. Okay. Similar way, you need to draw such a plot for every gas, for every range of operating conditions. So to avoid that difficulty, we have prepared certain parameters as reduced parameters we can call. Reduced parameter means every gas has its critical temperature and its critical pressure. What is the critical temperature and critical pressure? The point where latent heat is 0, okay, where the liquid is directly converting to the vapor without any dryness fraction in between. Yes, for case of water it is 220 bar and 374 degrees centigrade. Yes, like that every gas has certain critical temperature and critical pressure. Okay, what are we doing over here? The operating pressure is divided by critical pressure of certain gas. Okay, the operating temperature is divided by critical temperature of that certain gas. That way we can include all the things, all gases, okay, over here. If you see, these all the gases are included over here. Okay, from this plot we can observe 3 points. What we can observe? See, at very low pressures, okay, very low pressures here, irrespective of operating temperature, all gases are behaving like ideal gases because its compressibility factor Z is 1, this zone. Okay, that is. Yet the second point is at higher TR, at higher temperatures like this. At higher temperatures, irrespective of the pressure, the gas is operating or otherwise behaving like ideal gas. Suppose this case. Okay. TR equal to 2. That means the ratio of operating temperature divided by critical point temperature. That means the gas temperature is 2 times than critical point temperature. That means very high temperature. Okay. If it is water, okay, so we will be considering it as 700 degrees centigrade. Yes. So such a high temperature, suppose it is operating it as behaving as ideal gas. And second thing is that all gases are behaving as like pure real gases near to the this ratio. Reduced pressure ratio is 1. Okay, or around 1 over here. Yes. Okay, so this is actually this plot is about more close view of this. Okay, up to 1. This zone only we have taken. Okay, so because we will be using in our one of the problem also. Okay, up to 1. This is the reduced PR, means P by P critical equal to 1. Okay, suppose this is the steam look. Okay, this is the steam. We have taken the compressibility factor error. Okay, deviation from the actuality taken within the 1%. In that case, your steam as considering as ideal gas in this zone. Okay, considering as ideal gas in this zone. Like that. Okay, these 3 points we have discussed already. That is about decision factor, which gas is working at ideal gas, which gas can be considered as ideal gas, which gas can be considered as real gas. But however, whatever throughout our textbook, okay, whatever the examples are doing, whatever thermal power plant cycles or refrigeration cycles, okay, so we are considering it thermal power plant cycle or air cycles like diesel engine cycle or petrol means auto cycle. These all are considering it as also ideal cycles. Okay, now let us see ideal cycle properties. These you know very well. Okay, so see, PV equal to PV bar equal to R bar T. Okay, we are considering this both are equal. So Z factor also came from this only. Z equal to PV bar by R bar T, which is equal to 1. Yes. So that is the reason we are considering it as ideal gas behavior. Okay. And then these all you know. So this is internal energy. This is the enthalpy we are calculating. Okay. And respective things. This is the internal energy is du by dt. Okay. And simply how to take these all. U2 minus U1 equal to integral T1 T2 CVT. Okay. So came from this. You can understand these all. Similarly for enthalpy also. Okay. Once you observe over here, for case of the ideal gases, okay, Cp is greater than Cv. See over here. Okay. Because from dH, H equal to U plus RT, right? That we have seen in previous slides. H equal to U plus RT. Because instead of PV, we have substituted RT over here by following ideal gas law. Yes. Actually, H equal to U plus PV. That is only your enthalpy. Instead of PV, we have substituted RT. That again we are taking derivations on the all the sides. Okay. Differentiations. Yes. Then this thing is coming like this. Cp equal to Cv plus R. That means Cp is certain things higher than your Cv. Okay. Cp is greater than Cv. This ratio Cp by Cv we are considering it as K over here. Okay. Now, the Cp value of certain gases will be increasing with the temperature. See over here. For other gases like monatomic gases like argon, neon, and helium, this will be almost constant. Okay. However, for other gases like H2, CO, O2, steam, and carbon dioxide, okay, with increasing the temperature, the Cp will be increasing more. Okay, that is the reason combustion gases from any engine or any thermal power plant at high temperature having more Cp. Okay, if those gases are losing to the environment means efficiency losses are very high. Okay, because that is carrying so much of the heat because whatever the mass is going, okay, whatever the at the high temperature MCP delta T. Obviously, it is at high temperature. By the virtue of temperature itself, losses are very high. The CP capacity is also very high. Okay, so that's what losses are very high over there. And anyhow, the CP values are varying with respect to the temperature like this way. For other gases like monatomic gases, it is varying like this. And from the data also, we can calculate Cp value. Okay, this is the certain polynomial equation is given over here. Okay, so the in this polynomial equation, this alpha, beta, gamma, delta, and eta epsilon, these values you can get from your table 21 also. In your textbook, you can go to the table A21. Okay, you can see that. Okay? And then whatever the gas is there for particular gas, you will be finding out these values alpha, beta, gamma, delta. Okay, and then particular temperature, whatever the temperature is mentioned over there. Okay, suppose 200 2000 degrees centigrade. For case of carbon dioxide, go over there carbon dioxide table, get these all alpha values. Okay, and substitute this particular temperature, you will be getting the Cp value. Okay, that way Cp values also you can get, but anyhow in the problems wherever we will be giving, these values are clearly will be given clearly. Now the question is why Cp is greater than Cv. This is the last slide of our theory part. Can anyone answer me?
Sir,
Why?
at constant pressure, we have need to give extra energy for work done. That's why
Yes,
CP.
yes, yes. So we are saying constant pressure. Yes, that means to maintain the pressure constant when you are supplying the heat, obviously the volume try to expand. Okay, volume to maintain that pressure will be increasing if volume is not allowing. Yes, so to maintain that boundary should be moved. Okay, when boundary is moving means work is happening over there. Okay, simply if you take piston cylinder arrangement, pressure constant, heat supplying means volume will be increasing. Yes, that means piston will be pushing out. When piston is pushing out means you are getting the work. That means whatever the heat you are supplying, that heat is combined effect of increasing the temperature as well as producing the work. That is the reason Cp is high than Cv. Okay. So this is about theory part about properties of pure substances. Okay. Now we have one more hour. Okay, I have gathered very nice problems of 8 problems. Okay, so please solve the problem as like our previous tutorial. I'll be showing you the problem now, then I'll be giving you couple of minutes time. Okay, now my this teams problem also solved, this animation and all working. Okay, please try to solve the problem. After 2 minutes anyhow I'll be explaining to you. I'm changing my slides. So do you able to see my tutorial? Can anyone
Yes,
confirm
sir.
me?
Yes, sir. Yes, sir.
Okay, okay, thank you. Yeah, so this is the problem number 1. Okay, so here The animations and all are not required. This is for our understanding only. I'm starting this to explain you. Okay. Now, 5 cases are given over here. In these 5 cases, the question is about find out what is the state. Okay, what condition it is. Okay. Suppose the case 1 is 5 bar temperature equal to 151.9 degrees centigrade. Okay. So can you please go to table A2 or A3? Okay. At this pressure, what is the saturation temperature given over there? Can anyone tell me? So please be active. Okay. So because this practice itself you will be doing now itself in the class. Okay. Later on you no need to worry about how to see the steam table, how to use the formulas, how to calculate. Okay. So please go to the table at 5 bar. What is the saturation temperature? Please let me know. Since our working substance is H2O, so go to the table 2 and 3. So could you be able to open the table?
Yes, sir. Like it's given 151.9 degrees Celsius only.
Okay, so this is only one mistake we could have identified from the problem itself. Okay, this is actually not a two-phase. This is actually saturated steep point. Our point is exactly over here. Okay, our point is exactly wherever mouse point I am putting, that point only. Okay, that is saturated vapor, simply saturated vapor, nothing more. Okay, the point number 2 means B, 5 bar 200 degrees centigrade. Same pressure line. Yes, this is the same pressure line. Only thing is temperature is increased. Then obviously what you can mention, this is superheated vapor. Fine. Now what is next? 25 bar 200 degrees centigrade. Okay. Can anyone see what at 25 bar from the same steam table, what is the saturation temperature? Can you please tell me what is the saturation temperature?
224.
127.43.
How much is the saturation temperature at 25 bar? Not 2.5 bar, 25 bar.
224.
224. That means, so this line, okay, whatever this phase change operation will be happening for case of 25 bar, this thing, okay, at 224 degrees centigrade. But however, our temperature is 200. That means we are somewhere over here. Okay, we are somewhere over here. That means this is subcooled liquid stage. Okay. Now, what is the next thing? It is pressure equal to 4.8 bar and temperature equal to 160 degrees centigrade. Can anyone check at 4.8 bar what is the saturation temperature? At 4.8 bar, what is the saturation temperature? So I'm not able to open my tables actually. I don't have any other second computer with me. Okay, so I'm displaying this, right? So you need to open it and you need to tell me.
Like it is not given directly, so I was doing linear interpolation. It came somewhere at like 150.3.
So otherwise 4.75 would have been given or 5 would have been given.
Yeah, 4.5 and 5 is given.
What is the 4.5?
It is 147.9.
Okay, and what is the 5?
151.9.
150. Yeah, yeah. Even at 5 bar itself, 151, 159, whatever we have seen earlier, right? Okay, it is at 4.8. Pressure is slightly reduced. Yes. So temperature is even 1 point more than our case A. That means obviously this is superheated steam. Yes. So the next one is actually 1 bar means atmospheric pressure only. This is minus 12. You can simply say this is ice point only. Okay. That is about problem number 1. Finding out how to use the steam tables and finding out what stage it is. Okay. Now problem number 2. So please try to solve it. I'm giving you a couple of minutes time. Okay. This is also water. Yeah, water. Use the tables and let me know. Anyhow, these presentations, both the presentations, I will be loading. Okay. So if you are, if few students are not able to understand very well, you can repeat it. You can repeat by yourself. So what is the problem about? A container is there. The container volume is 0.2 meter cube. Okay. Initially, the chamber is at 5 bar pressure. In that, 50% dryness fraction is there. That means 50% is steam. Okay. Quality. Then the heat is supplying. So finally, 100% reach it to the 100% vapor. Okay. Then we need to calculate that. See, this is the thing. Initially, this is okay. 50% steam, 50% water content. Then finally, reaching to the this stage wherever it is 100% steam. What is the pressure over there? Okay, that is the question. Then how will we solve this problem? So initially we have to calculate from the table A3. We will be calculating like this. VF1, you know, how do you know VF1 and VG1? Okay, at 5 bar pressure, okay, initially at 5 bar, right? At 5 bar pressure, we are taking VF and VG. Okay, these two are available from your data book. Okay, and this point is 0.5. Okay, so this value from your data book, and even this value is also from your data book. Okay, and 0.5 given in the problem. That way its specific volume is 0.188 meter cube per kg. Fine. Then its mass is like this. Its volume is given. Its specific volume we have calculated. Volume by specific volume obviously giving you the mass. Yes, the mass. Then since that is rigid container, okay, rigid container, volume would not be changing. Yes, so considering both the volumes are same. Okay, and now the same volume, simply the same volume, okay, you have to match with certain pressure in the steam table where you are getting in the saturated vapor. Okay, this value you have to check wherever you are getting in the saturated vapor at what pressure. Okay, there you will be finding out this particular pressure value. So otherwise now we know answer. Simply go to your steam table at 10.5 bar. What is the gas volume? Means saturated gas volume. Can you go and check? Is it matching? At 10.5 bar. So can anyone please confirm me?
Sir, in table there is only pressure up to 8 bar is given.
No, 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 it is not like that. Otherwise you can see from this table, right? A2. Do you able to see this? So here it is 10. Okay, this is 10 bar. Okay, here this is 0.1941. Okay, this is 10.5, means after this. Okay, so volume is reducing, right? So if you interpolate appropriately, it will be coming somewhere over here. Would you able to understand? Fine. Shall I move to next
So can you please once
problem?
scroll this table so I can see the top list of the which things are given?
Yeah, up to critical point it is given 220. This is the table number 2. Okay, or even in the table number 3 is also, this is with respect to pressure, that is with respect to, see here, pressure. Okay, so we are coming over here 10. This is table number 3. This is table number A3. Okay, in the page 722, a 10 bar pressure, saturation vapor, that is completely saturated vapor, right? Why? Because the condition is given This is 0.1944. Okay. Then you can interpolate. Or in the table number 2, it is very easy because here this is 10, this is 12.54. Okay. At the 10 you have 0.1941. At the 12.54 it is 0.565, 0.1565. Okay. If you interpolate, you will be getting pressure 10.5 bar and your volume is the same volume. Okay. Same volume of this 0.1880. Fine. Okay. So anyhow, I'll be sharing this presentation, right? You please practice. Okay. So problem number 3. So please try to understand and try to solve it. So in the coming class, next class, I'll be teaching engineering equations solver. Okay. So that is also part of our syllabus, and certain problems by feeding the equations. Okay. So many equations will be there. Once you feed the equation, okay, you no need to derive the equation. Then after you no need to use certainly feed the value, and then finally you will be getting the answer. It will means in case of conventional method, pen paper method, we will be doing this much of lengthy procedure. Okay. Once you learn engineering equation solver, you will be feeding the equations. Okay. So you are not required to follow engineering equation solver, but you can write your own code in the MATLAB also or C also. That is very simple thing. Okay. But here the course itself is suggesting us to teach you engineering equation solver. Okay. In coming 1 or 2 classes, I will be teaching you engineering equation solver. So please solve this problem. So solving the problem would take little long time. Try to understand the problem. Okay. Then manage. Okay. How to solve the problem. So meanwhile, I'll start explaining this. Okay. So what is the problem about? Initially, there is steam with volume of 1 meter cube. Okay. that is at 7 bar and 500 degrees centigrade. Okay, it's losing heat to the surrounding. Okay, then you need to find out at what point the condensation, initial point of the condensation is starting. Okay, then when it reaches to the 0.5 bar, what is the volume that you have to find out. Yes, this is the initial condition. Yes, 0.7 bar and 500 degrees centigrade, 1 meter cube. Yes, this is the 0.1. Okay, so at 7 bar, what is the saturation temperature? Can anyone please see from the table? Pardon? Can you please be loud? Actually, I'm not able to hear you.
165.
165. That means whatever this temperature is there, that is superheated temperature. Okay, very high temperature. Okay. Now, condensation starting means where? Exactly at saturated vapor. Okay. When from the saturated vapor, when you move little this side, latent heat zone side, then condensation starts. Condensation means what? Forming the liquid content. Yes. So from this point, at what point it is starting condensation? Okay. You need to characterize these points. What are these points? Okay. Then after, you need to find out at 0.5 bar. This is the 0.5 bar line. Okay. Then straight away coming over here, what is happening over here? Means what are the characteristics of the fluid over here? That we are finding out. Okay. Given this point and these 2 points, we will be calculating from the steam table. Okay. Now at this point, okay, the specific volume we are calculating. Okay, this is the volume of the container. Okay, but however, specific volume at this point from the steam table, where you may need to go superheated steam tables. Okay, superheated steam tables, many tables are there. From that, you will be calculating its specific, even this point volume from the table A4 you can take. Okay. So wherever at this point, which point, this point, okay, is happening, because this volume is same. We are maintaining the specific volume as the same. Okay, that's what V1 equal to VA equal to V2 equal to. This is the value we are getting from this point. Where will you get this point value? The same 7 bar pressure, 500 degrees centigrade. You can go to the table and then you will be finding out this value. Okay.
But sir, at 7 bar, the specific volume means at saturation point is different, sir. It is not 0.5.
Let me open my tables also. Table A4. Yeah, actually 7 bar might not be given to you. This is 7 bar. Okay, this is 7 bar table. And what is our temperature? 500 degrees centigrade, right? This is 500 degrees
Sir, it is
centigrade.
0.7 bar, na?
Huh?
0.7
Oh
bar.
yeah, 0.7 bar. Yeah, I'm sorry. Let me go there. This is 10 bar. This is the 7 bar. Is it? This is the 7 bar table. Okay, and this is 500 degrees centigrade. This is the value. Yes? Clear?
Yes, sir.
Okay, fine. Let's go back to our slide. Okay. Okay. Now, the same volume we are considering, we are just drawing the line down. Wherever it is touching to that temperature is 140. Okay. You can take from table A2. Okay. Check this point also from the table. Now you need to calculate a dryness fraction for the state 2. Okay, state 2 means final state. In between state we have considered A, the final state at 0.5 bar. Okay, so there you have to calculate. Now you know 0.5 bar pressure is given. So for the 0.5 bar you will be calculating, you will be finding out from the data table the saturated liquid volume and specific volume, saturated gas volume. Okay, and then you have V2, you know, because considering V1 equal to VA equal to V2. Okay, from that dryness fraction you are calculating. Okay, that means this much amount of gas is there, this much of amount of gaseous stage or vapor stage is there, rest of all condensed to the liquid. Okay, this much of amount of liquid because very low pressure, right? Then what is the total mass means? This is the total mass. Okay, mass equal to volume by again specific volume, we will be getting this. Okay, fine. This is about the problem, simple problem, you can understand. So step by step actually degree of complication also slightly increased. You will be finding out more interesting problem. Okay, this is as like your first problem. Okay, so only thing is many data or different gases are given. So please try to solve this problem. I'm coming in 1 minute. I need to. Baba, tell me. No, Baba, class going on. Half an hour more. Yeah. So here the different fluids are there. Refrigerant 134, refrigerant 22. Okay, ammonia. That means different table we have to use. Okay, let us see. So anybody solved any part of the problem? If you have solved, please let me know. If you want time of 1 minute or 2 minutes, I would like to give you more. Okay. The first one is about a refrigerant. Yes. It is at 60 degrees centigrade. Yes. Given condition was it is at 60 degrees centigrade and its volume, specific volume 0.072 meter cube per kg. Okay. And you need to calculate its pressure and enthalpy. Okay. Let us see. From table A10. Okay. Table A10 is giving you the data about this particular refrigerant of 134A. Okay. And there your gas temperature means saturated vapor specific volume is this much. Yes, saturated vapor specific volume is this much, and given specific volume is what? Even almost 5 times than this. Yes, that means when the volume will be increased at the constant pressure. Okay, so that means it is superheated region. Yeah, so from that we can conclude, since the given volume is very much greater than saturated vapor specific volume, okay, then we can conclude it as superheated vapor. Fine. Okay, then once you interpolate according to the data, okay, in the table A12 also for this particular, okay, then you can get at 3.63 bar and its enthalpy value. Okay. You check with the data and even the tables, you'll be able to find out easily. The next one is like ammonia. Ammonia is at 8 bar. Okay. And its volume is this much given over here. Okay. From the table, its volume should be which volume? Gaseous volume. Means specific volume of saturated vapor should be 0.1596. Okay. But however, the given volume is very much less than that. Okay. But that is in the range actually, in between. You need to check your liquid volume also, saturated liquid specific volume, saturated liquid specific volume. When you compare the given specific volume with saturated liquid specific volume and saturated gas specific volume, the given specific volume is coming in between. Okay, given specific volume is coming in between. That means somewhere this point. Okay, somewhere this point in the mixer point. Okay, in the latent heat zone it is somewhere in the mixer point. So for this particular ammonia, okay, and even for case of 8 bar pressure, the saturation temperature is 17.84. Okay. Then from this data, Vf is available, Vg is available at 8 bar pressure. Okay. Then we will be calculating this dryness fraction. Even the given volume also given over here. Given specific volume is this. Okay. This is the dryness fraction. That means what? 0.02. Okay. Initial stage of evaporation it is actually. Okay. That's what this point is, closer to the saturation liquid line. Okay. Then what you need to calculate over here? You need to calculate internal energy. Okay. Internal energy again This formula also we have seen in our class slides just now before this tutorial. UF. At this pressure from the data book, okay, of this table, you will be calculating liquid specific internal energy of the liquid, specific internal energy of the vapor. Dryness just now you have calculated. Okay. By taking these all things, you will be calculating mixer properties like this. Okay. This mixer property is this much. Now what is remaining? And again another refrigerant, that is 22. Okay. Refrigerant 22. These refrigerants actually chlorofluoro refrigerant we call based upon that numbers. These all you will be learning. Okay, those all will be unnecessary matter over here. Anyhow, we are just remembering refrigerant 22, refrigerant 134. Okay, this is at minus 10 degrees centigrade. Okay, its internal energy is given to you. This table for this particular refrigerant table is given as V7. Okay, sorry, A7. So in the A7, for this particular temperature, whatever is given over here, okay, and we will be calculating both specific internal energy of the liquid as well as specific internal energy of the vapor. Okay, so here the given specific internal energy is falling between these two. Okay, that means again the mixer means this point is lying in the mixer zone, the latent heat zone. Okay, and again what we need to do, we need to calculate dryness fraction over here, means x. Okay, this x you can calculate from anything. You don't need to calculate from u only, means v only. V means the specific volume. You can calculate from enthalpy also, x. You can calculate from internal energy also. Okay, why? Because for anything this is the formula. Yes, this is the formula. Yes, if it is internal energy, all the words will be replacing by internal energy. If it is a specific volume, these all the words will be replacing by specific volume. Okay. So now by using this internal energy formula, we will be calculating this dryness fraction. This dryness fraction is 0.879. That's what this point is close to the saturated vapor line. Okay. Means roughly we are putting over there. Then now we are calculating the volume, means specific volumes. This is the specific volume. Okay. That is about problem number 4. Okay. So problem number 5. So like this we have 8 problems, but 8th problem is very small problem. Okay. So we still have 25 minutes time. Okay. So let us see problem 5, 6, 7 in detail. Please try to solve this problem number 5. I'll give you 4 minutes time.
Sir, I have a doubt that
Yeah.
is this kind of question are come in our exam that
You see, exam is actually usually thermodynamics exam. The paper will be setting by common paper. Internal means mid exams and all I will be conducting. Okay, but for any section, final exam will be conducting by in group. We actually thermodynamics we are handling by 4 sections. Professor Aditya and me and Professor Subran Surai, Professor Chirag Kalelkar. Okay, for all 4 sections, question paper would be common. That is not yet finalized. Okay, I don't know, but usually it was like that earlier. In that way, actually, all the topics should be covered by me. That's what I'm trying my best to teach every point. Okay, because tomorrow, once you see the paper, you would not be feeling like Professor Reddy has not taught this point. Okay, that's what I'm trying my best. I'm covering whatever the syllabus 100%. Okay, this kind of, yeah, even the steam tables you have to use.
like we have to use such a data from the table continuously when solving.
Yeah, we have to use. You have to use. Even when I was in BTech, I have used. Even in case of GATE exam, also these tables. Yeah, in GATE exam also these kind of tables would be given. In every exam also table would be given to you. If it is conventional exam, right? You will be writing in here by attending in examination hall in IIT. Okay, stream table will be provided to you.
Okay, sir. Means time duration will be according to the caution. Like it takes some more time
Obviously,
to.
yeah. Accordingly, the time will be setting like that. But this is not anything new thing actually. This is common phenomena in the history of thermodynamics.
Okay, sir. Thank you.
So once you habituate to see this data, then yourself you will be finding out. Yeah. So instead of that, going to the textbook and scrolling down, just take a printout of this and keep with you. Hmm. Okay. So initially the water is with saturated liquid. Okay. And then here the saturated liquid means so about to start evaporation. Okay. And then it is allowed to get cool. Okay. To other pressure. Okay. To certain other pressure. So because of that certain mixture is forming, that is like this. Vapor and liquid are in this proportion. Okay. Determine the heat transfer. Now we are so far what we have calculated, mixture properties only we have calculated. Now we are calculating heat transfers also in these two problems or three problems. Okay. So this is the first law of thermodynamics, as you know, and many times we have assumed these two we are not considering. Okay, in case of thermodynamics problems, kinetic energy and potential energy. Okay, these two are zero. Okay, and here the problem itself is saying this is the rigid container. Okay, so that's what work is also zero. Then whatever heat transfer is, loss of its internal energy or gaining whatever it is. Okay, that's what Q equal to delta U. Okay, U2 minus U1. Okay. Then what are we doing over here? We are calculating its respective values, okay, of the fluid. Anyhow, the point 1 is given, right? Point 1 is given, okay, and its total mass is given. Yes. And now according to that, U1 equal to UF1 is this much. From the data book also you can take this. Okay. That is anyhow state 1 is given in the problem itself is saturated liquid. Okay. It is saturated liquid. And volume is obviously same. Yes, volume is not going to change. Okay. So from that we have calculated over here the volume. Why here? This is with specific volume and we are multiplying with mass. Then only it is becoming volume. Okay. So now we are using A2 table. Okay. And these all the details. VF2 values we are taking. Okay. And respectively we are calculating U2, U1. Anyhow, U1 we know from the beginning over here. Okay, that is a 2000 kg mass is there in your container. Once you know these two, then Q will be able to calculate. Okay. So only thing is you have to understand the problem. So this is our attempt to identify how to use both state variables as well as the properties as well as heat calculation. Okay, that is the simple problem. Now the problem number 6 and 7 are the more advanced version of this problem. Okay. Cycle is also involved here in the 6 and 7 like this. I think here cycle is not involved. Okay, in the next problem cycle is involved. Eighth problem is very simple. Okay, that means we have two problems only, 6 and 7. Please focus. Yeah, try to solve. Okay, here this is actually as like we have solved in our previous tutorial. Okay, so this is simply at this point to this point. Okay, it is following PV power n equal to constant. But however, n value is not given. We are going to calculate n value over here. The initially it was minus 40 degrees centigrade. Okay, and it is mentioned that this is the saturated vapor at that point. Okay, and finally we are reaching to 6 bar and 80 degrees centigrade. Okay, now we need to calculate work and heat transfer from this process. Okay, here the polytropic work, as you know, we have solved in our previous tutorial also. Any work is equal to integral 1 to 2 PV. Okay, PdV. And then here, for case of polytropic, once you solve this particular derivation, okay, so P2 V2 minus P1 V1 by 1 minus n. But what about the n value? Okay, n value we are calculating by this method. Okay, P2 V2 power n equal to P1 V1 power n, but applying all both sides, so logarithmic, okay, and separating and then forming. Okay, n equal to ln P ratio ln V ratio. Okay, these values we are taking. This is the tables for propane and propane tables A14 and A18. Okay, we will be taking the data. These two pressures we know. Okay, 6 bar and 1 bar. The respective specific volumes we are taking over here. Okay, respective specific volumes we are taking. Then n value we have calculated. Now use this n value over here. Okay, and work we will be calculating. This is the work. Okay, now as you know, it is your first law of thermodynamics. Okay. Then at those points you will be getting these U2 U1 values from these tables. Okay, and then you will be calculating this. This problem is about only nothing how to calculate this n value if it is not given from the data table. Yeah, we have done this through data table, right? Earlier in our tutorial number 1, wherever this polytropic process are there we have mentioned n value equal to 1.3, 1.4. Okay, if n value is not given, once you know these tables and all, then how to get n value, that we have seen over here. It's a very simple problem. The problem number 7 is with cycle, is very interesting problem, and last problem also. So please try to solve by yourself.
Sir, can you please show the result of last problem, sir, once?
Fine.
Yes, sir.
Okay. So this is one cycle. In this cycle, the working fluid is ammonia. Okay, there is 2 kgs of ammonia that is undergoing a cycle with 3 processes. The process 1 to 2, okay, is constant volume process. 2 to 3 constant temperature process. Okay, next one is constant pressure process. Okay, here we need to calculate heat transfers and all. Okay. So initially the cycle is starting, right? So here is the cycle coming in the next slide. Okay. The state 1, wherever it is starting, it is given in the problem itself. That is P1 equal to 10 bar. Okay. There its dryness is 0.6 to saturated vapor. It is moving. The process 1, 2. Okay. So ammonia is representing in table number A14. Okay. State 1 at dryness fraction 0.6, we are calculating internal energy. Okay. So in the same table, we will be going over there, and then for the 10 bar pressure, we will be calculating I'm sorry, liquid, saturated liquid internal energy, saturated vapor internal energy. Okay, the data is readily available in our table for 10 bar. Okay, then dryness is given over here. So at state 1, internal energy we are calculating. Fine. Okay. With the same data from the same table at 10 bar pressure, okay, you can get as like you got specific internal energy of the liquid, specific internal energy of the gas at saturated. Volumes also we are getting. Okay, then volume also we have calculated. State 1 is completely defined. Now state 2. Okay, state 2, see the process 1, 2. In the process 1 to state 1 we have defined. State 2 we are going to define. Here we have mentioned it is a constant volume. That is the reason volume is same V2. The same volume we will be considering. Okay. Then, but however, this is reached to the saturated vapor completely. Okay. It is reached to the saturated vapor. That's what this is we are taking. And then U2 we are calculating. That is also directly available from the table since it is saturated stage. V2 we are directly taking from the table. Okay. And respect to temperature. And state 3. That means when you want to go state 3, 1 to 2 completed, 2 to 3 we need to go. 2 to 3 means this is the constant temperature process. Okay. And here heat is also given over here. Okay. Constant temperature process. And the same temperature we are considering since constant temperature, right? This same temperature we are considering over here. Then at the same temperature and the same pressure, we are calculating U3 from the table. This is actually you need to keep the table besides you. Take the printout of that and follow this particular tutorial. Okay, and match each other. Then you will be able to understand. Once you understand very well, then it will be very happy. See, this is the cycle 1 to 2. What is this process? Constant volume process. Okay, in the constant volume process, and then this is constant temperature. Yes, or you can see over here. This is constant temperature. Okay, then you will be coming back to the 1. Which process? Constant pressure process over here. Okay. So all the states in our previous slides, we have calculated internal energies and specific heats. Okay. So we are substituting all of them in case of your first law of thermodynamics, energy equation we can call it. Yeah. For the each process. Process 1, 2, U1, U2 you have calculated. Since that was constant volume process, this is the constant volume process, right? Since it was constant volume process, work is 0, internal energy you have calculated. Then heat transfer we are calculating over here. Process 2, 3, isothermal process, right? Okay. So they have given over here 2, 3. Q23 is given in the problem itself. Okay. And the work we are calculating. Process 3, 1. Okay. Process 3, 1 is constant pressure process. Okay. That's why pressure is constant, volume is changing. Okay. That we have calculated. This is the work. Okay. And then this is the internal energy part this side, and this is heat transfer, and this is the work done. Okay. So we have summarized, or otherwise we have added these all the things, work derived in all three process. Okay. Finally it is coming positive value. So we can conclude this cycle is power cycle. This is about problem number 7. Okay. So problem number 8 is very simple. So this is about compressibility factor, that Z we have calculated, we have seen, right? So here certain data is given. Okay. So this is the operating pressure is 200 bar, and even the temperature is 470. What are we doing over here? This pressure by critical pressure. Okay. This is for water. Yes. 200 by 220, 470 divided by 374. Then you will be getting reduced pressure. See, this is the reduced pressure here, and even this is the reduced temperature. Okay. This is the given temperature, and this is your critical temperature. Then ratio we are getting over here. Okay. For these two values, this is the table, or this is the plot. Yes. This is the reduced pressure. These are different temperature scales. Okay. Now this is 0.9, means around over here, and this is 1.15. This is 1.15 curve. Yes. So at this point, compressibility is coming like this. Okay. Compressibility factor 0.79. Okay. For this curve, this is the point. Okay. This is the point. Okay. 0.79. Now here actually in the problem it is asked to you calculate from the table, means not table, chart, as well as from the steam table. Okay. How will you calculate from the steam table? At this temperature and at this pressure, okay, we will be calculating Z value. Pressure we know. For this pressure and temperature, you will be finding out your specific volume. Okay, that is only thing we are getting, specific volume. Then R value we know. R is what? Universal gas constant by molecular weight. Okay. So then once you do this at this temperature, this calculated value also coming under 0.79. Okay. Both the ways you can do from the table also. But however, this is not perfect ideal gas, close to the ideal gas we can consider. This is about problem number 8. Okay. It is completed. Okay. I am posting that theory slides also, and as well as this tutorial also. So please take printout of all the tables, keep besides you, and practice this. Once you practice now, okay, that same standard will be there with you forever. Okay. Not only now, even applied thermodynamics or otherwise, we have Rankine cycle actually later. Okay, in some chapter there also we will have to see these all the things, the tables and all. Okay, so this is a bit uh, confusing kind of thing. Okay, once you practice very well, that will be very easy. Okay, thank you. Thanks a lot. So if you have any doubt, you can ask me now, or you can straight away write in the Teams also. I'll be responding to you. Fine. So can I
Yes,
close?
sir.
Okay. Okay then. Thank you. Thanks a lot.
Thank you, sir. Thank
Yeah.
you, sir.
So Wednesday we
Thank you,
don't
sir.
have. Yeah, Wednesday we don't have class because Republic Day. Okay, let's meet in Thursday class. Let us discuss about engineering equation solver. Yeah.
Okay, sir.
Thank you. Thanks a lot.
Thank you, sir.